Hopefully it's obvious.
I got it. As
Okay, thank you.
opposed. Yeah, no problem.
Oh, ironically, I see the record button. I don't see.
I don't know why. Maybe because I shared screen, it moved. I don't know. I wasn't able to find it.
Oh,
Thank you.
yeah. It was under more, and then there was a recording in the menu,
Okay.
and now it shows up on the bar.
Okay.
Yeah.
Great. Okay. Well, maybe I can, we're a few minutes after the hour, so maybe I'll get started. Um, so my name is Christina Williams. I'm on the community science team, and I'm gonna host today's Rubin Science Assembly. And the topic is galaxy photometry and shape measurements in Data Preview 1. So I have a few slides in the beginning that include some announcements and other things before we get started with an actual tutorial that demonstrates how to use these measurements in the DP1 data products. All right, so first I'll spend a few minutes with announcements, and then I guess maybe it's going to be in a few minutes, I'll start the tutorial on galaxy photometry and shape measurements. And so questions are welcome at any time. Just raise your hand in the Zoom chat. Someone from the community science team will moderate the questions, or I also have the participant list up so I can see if someone asks something. And so interruptions are fine. If you have questions, we can address questions in the middle. That's totally fine. Oops. Sorry. Okay. All right. So some announcements. This is the first Rubin Science Assembly for the fall semester. So we have some announcements that are left over from the summer in case you missed it. So rubinobservatory.org has all of the Rubin first look images, which were released in June. And they're spectacular. You should go check them out if you haven't seen them already. They were in the press, and they have a lot of great visualization tools available to navigate through the data and see for yourself how wonderful it is. Um, in addition to the Rubin First Look images, Data Preview 1, which is a collection of data from the commissioning run last year, was released for science use on June 30th. And so you can go to this website, dp1.lsst.io, to get more information on how to access Data Preview 1 and what's included. And so the data that I'm going to show today in the tutorial is a part of Data Preview 1. And so you'll get more information on that also from this website. So shortly after Data Preview 1 was released, we had a Rubin Data Academy this past summer from June 30th to July 3rd. If you were there, that's great. If you were not able to make it or didn't know about it, we have posted recordings and slides and materials from the Data Academy. And so this is a great way to get caught up on what is available in Data Preview 1 and how to access it and use it for science. And so we encourage you to go look at this website on GitHub where we've stored all the materials. I think I saw a message in the chat. Yes. Okay. Oops. Okay. So some more announcements. We have a bunch of upcoming events, and they're all listed at the rubinobservatory.org website that's listed here for events. And so you can find out some of the tutorials and other things that are up and coming in the next few months. So I'll just highlight a couple of upcoming Rubin Science Assemblies. The next two ones that are coming are going to be in October. We run these Rubin Science Assembly tutorials every 2 weeks. And in the off week, the same time slot, we have a drop-in session so people can come and ask questions or just listen in on other people's questions. And so it's sort of office hours to to interact with the community science team for Rubin related and data preview related stuff. So upcoming, we have a tutorial on October 2nd about cross-matching with user uploaded tables. So this is an exciting feature that I think people will make use of so that people can identify the Rubin data for their favorite targets. And then after that, in mid-October, we have astrometry and the world coordinate system in DP1. So another announcement, about a month ago or a month and a half ago, we had the Rubin Community Workshop and in Tucson, and we have the slides and recordings available at this website. This is also a great resource to sort of find out what people are working on now, and review some of the discussions that were happening in at this workshop if you weren't able to attend, or if you attended and you want to remind yourself of something. All these resources that are available. Okay, so if you're new here, welcome. We have a list of resources here that might be useful for you. So the Rubin Science Platform is the primary way to access the Rubin data. It's at rsp.lsst.io. And so you can go there to get an account. For the Rubin Science Platform so you can access the data. We have resources for learning about Data Preview 1, which is the current data set that we're encouraging people to use. This is commissioning data from last year using so it's real photons on sky rather than simulations. The simulations are still available if you want to work with those. And then we have some general resources for information. So we have this rubinobservatory.org for scientists site, and we also have the community forum, community.lsst.org, which is a venue where you can ask questions and get help from the Rubin staff and also community users who may know the answer to your questions. So this is a great resource. We encourage you to use it. And quickly, I have two more slides here. One is I want to make everyone aware of the Rubin Users Committee. And the Rubin Users Committee solicits feedback from the community about the Rubin data product. And so what part of their charge is to make recommendations on how to improve this. And so it's useful for them to be in touch with the community. So we encourage you to follow what the users community is doing and interact with them. And there's a bunch of venues here where you can do that. I also want to point you to the Link Frameworks office hours. So Link Frameworks is a mission to enable scientists to develop scalable and productionized software and algorithms in collaboration with the broader community. So there's a bunch of resources here. They also host office hours where you can find out what's going on and ask questions there. And so they have there's a summary of some of the projects that are ongoing. For example, photometric redshifts and other things that are sort of outside of the scope of the standard data products, but are still needed for science by the community. All right, so maybe I'll pause here briefly for any questions about the slides I just showed and the announcements. And if not, then I can proceed to the tutorial, but please raise your hand if you have any questions. Otherwise, I'll keep going. All right, if questions come up, you can also ask later. So I'll just get started with the tutorial. So to access the tutorial, I'm going to look at two published notebook tutorials that are available in the Rubin Science platform. So first, we're going to go to data.lsst.cloud, which is the location of the Rubin Science platform. So if you already have a Rubin account, you will recognize this page. If you don't, that's fine. You can also just follow along. I'm going to sort of demonstrate the notebook in the web browser, and I'm sharing screen, so it's not necessary to have access yet, but I'll just show how to access it in case you want to follow along on your own machine. So first we log in. If you already have a Rubin Science platform account, then you have an identity provider, so you have to select this to log on, and that should already be set up for you. So to access the notebooks, we're going to click on the notebook aspect button in the middle of the landing page here. So I'm going to click on this notebooks. And we're going to load some images and catalogs. So I'm going to pick a large container size for the server, and I'm going to load that up. And then we're going to wait for a second while that loads up. All right, great. Okay, so this is the landing page in the notebook aspect of the Rubin Science platform. The notebooks, the tutorial notebooks that are released by the community science team are all available in your account already. So you go to this tab called tutorials, and this drop-down menu has a number of options. And so these tutorials are using DP1 data preview 1 data. So we're going to go to data preview 1. And the two notebooks that I'm going to demonstrate today are science demos. So I'm going to go to this 300 level category of notebooks. And here you see another drop-down menu that shows a range of topics for which we have science demo notebooks. So we're going to go to the Galaxies, 303 Galaxies. So the first thing I'm going to do is open this Galaxy Photometry notebook. Okay, so here you see the notebook. So I'm going to run through this notebook and also sort of show some here. I'm going to actually change this tab so you can see this is on the left here. Now I'm showing the table of contents for this notebook so you can sort of see what's coming ahead. So since I have to review two notebooks today, I'm not going to go through both of them in their entirety. So I'm going to skip over a couple of sections in this photometry one so that I make sure I have time to get to the shapes notebook. So first, the beginning of these notebooks has some preamble where we provide some information, including some introduction. So in this case, this notebook is focused on galaxy photometry in DP1. So the Rubin LSST pipelines will automatically measure photometry from sources and objects in the data set and store these in different tables. And so we're mostly going to be working with the photometry in the object table, which is the table made from deep coad images. So these are the deeper stacked images that accumulate over the LSST survey lifetime. So these are the deepest images that are available, and they're basically static field objects. So they are, galaxies, stars, things that don't change regularly on the sky. So the first thing that we're going to do is import some packages. So this is going to include some standard packages like NumPy and Matplotlib, but also some of the Rubin LSST pipelines. In this case, I'm also going to import this scipy.stats package called binge statistic, just because it helps us to sort of visualize. Anyway, I'll get to that later. So first, we're going to start the TAP service. So the TAP service stands for Table Access Protocol. So if you're familiar with other virtual observatory services, then this works the same way. You can use the TAP service to query catalogs in the Rubin data set, and it will return objects from tables in the Rubin data set. So we're going to initiate the TAP service so that we can use this to query objects. And the first thing we're going to do is just look at the different types of photometry that are contained in the object table. So like I mentioned, the object table is a catalog of sources that have been identified in the deep coad images. So the first thing we're going to do is just query the object table for columns that contain the word flux. So first I'm going to set up this query where I'm going to ask the TAP service to return the columns in the schema for the DP1 object table. And then I'm going to ask for all of the columns that contain the word flux. And this is going to help us just see how many different types of photometry there are in the object table. So this is a list of all the photometric measurements that are there. So you can see there's a lot of them. So I'm not going to go through all of them in this session because not all of them are applicable to galaxies. So I'm going to focus mostly on galaxy science here. I just want to point out some broad categories. So this one is aperture fluxes in different circular aperture sizes. We have fluxes that use different types of galaxy shape models. So this one, BD flux B and D, are assuming a bulge or a disk morphology. There's a few things I'm not going to talk about. There's the C model flux, which is very important, and I'll talk about that later. That is, if you're familiar with SDSS, this is a type of galaxy photometry that was used in SDSS that is the sum of two Sursic models. I'm going to skip over some of these other things. GAAP is another measurement that I think will be useful to people. So this is sort of, I forget exactly what it stands for, actually. But it's a type of sort of PSF matched photometry, but it's a faster algorithm than trying to PSF match all of the images because, of course, Rubin has lots of images, and so PSF matching in order to do photometry is not uh, it's not a very computationally efficient thing to do. So we have this shortcut that sort of approximates PSF matching so that people can do color analysis without having to worry about PSF effects. And then there's the Cron photometry, which some of you may be familiar with. You can measure an ellipsoidal shape of a galaxy and then use an ellipsoidal aperture based on this. And Cron photometry is a way of doing that, so I'll talk about that later. And then we also have a single Sirsic flux measurement. And of course, there's also PSF flux measurements in here, but those are mostly applicable only to stars, and so I'm not going to talk about that here. Okay, so just to let you know, there's also some catalog entries are stored as magnitudes, not just flux. So the units of these flux measurements are all in nanojansky, but there are for PSF fluxes and C model fluxes, they also store magnitudes, AB magnitudes in the object table. So these, because this is commonly used, and then you don't have to convert to magnitudes if you want to use that. Okay, so the first thing we're going to do is select a galaxy sample. So if you're familiar with Data Preview 1, you will know that there were 7 targets on the sky for Data Preview 1. And so we're going to look only at the extended Chandra Deep Field South. So this is, you may also know this field as Good South. It's a very well-studied, well-targeted extragalactic field that was mapped in DP1. So this is the RA index. So I'm just going to set the RA index of the ECDFS. So we return galaxies that are contained in that field. And actually, the reason we're using this field, I should mention, is because it is one of the deepest and most complete data sets that was taken in DP1. So all 6 filters are covered, and the data it's some of the deepest data that we collected in commissioning, and so this makes it a good use case for galaxy science because we need to be able to detect faint objects. Okay, so I'm going to run this query now. This is a very large query. There's a lot of keywords that I'm requesting be returned from the object table. So I'm just going to highlight a couple of the things that I'm going to talk about. So not all of these are, I'm going to talk about these, but some of the things just to point out what I'm going to ask for. So I'm going to ask for the object ID, the RA and DEC of all these galaxies. I'm going to ask for the Cron flux and error. I'm going to ask for the C model flux and error, and then I'm going to ask for this GAAP flux. And GAAP, like I mentioned before, is the one where you can use it to do color analysis of galaxies because the PSF effects have been sort of homogenized. There's a number of GAAP measurements in there. I'll talk about that later. We're going to mostly focus on this one that has sort of been optimized. I guess it hasn't been optimized. It's the 1.0 aperture GAAP flux, and it's been sort of demonstrated that this one seems to work it seems to be effective at measuring the color across, a wide range of science applications. And so this one's very broadly usable. Okay, some other things I'm going to point out are these flags. So the object table has a number of flags in there that enable you to sort of quality control some of the measurements that come out. So we're going to actually request, in this case, that we return only objects that have been flagged as having good quality measurements, like I show here. So we're sort of enforcing that the return of this query has flags for the photometry equal to 0. We're going to request also that objects have this extendedness parameter of 1. So this means that these are not point sources, but these are extended objects, and so they're galaxies. And then, we have to do a spatial query because the catalog is sort of spatially sharded. And so if you don't include a spatial query, it will take a really long time to complete. So we're going to do that too. All right, so I set up this query. I'm going to send this query to the tap service and then it's going to compute and send us a table back. Um, so the search has completed, and now I'm going to store the query results into this table called tab. And so here you can see, I've printed that out here. You can see all of the keywords that I requested have been returned. And within the spatial search, given the parameters I requested, we got about 3,400 galaxies returned to us in ECDFS. Okay, so now I'm just going to, sometimes it's easier to work in magnitudes, so I'm going to convert all of these fluxes into magnitudes here. Um, so especially when making color magnitude diagrams, this is it's nice to have these on hand. Okay, so then I also mentioned I mentioned that there are some shape parameters in the object table also. So we're just going to grab, for the purpose of this notebook, we're just going to grab a couple of those. So we're going to grab the cron radius, which is I cron rad, and we're going to grab the Cersic index. So I'm doing that here. And I'll talk about that a little bit later in the next notebook. All right, so the first set of fluxes that we're going to look at are total fluxes. So these are fluxes that are measured on the objects with the intent of sort of capturing all of the flux that comes out of the galaxy. And so at some point, light profiles of galaxies will go below the noise limit, and so you sort of have to extrapolate to figure out the total fluxes, and these are useful for measuring things like absolute values of things like the luminosity of a galaxy or the stellar mass of a galaxy. So there are a number of total flux measurements. One of them is the Cersic flux. So we fit a Cersic profile to each galaxy. And the Cersic flux, then you integrate over the whole light profile of the galaxy and you get a total flux for the galaxy, assuming a Cersic model. There's also these bulge disks. So the Cersic model leaves the Cersic index free. So the Cersic index is a description of how shallow or steep the light profile of the galaxy is. And so you leave that parameter free so it sort of, will use the galaxy light profile itself to measure the Cersic profile. We also have, in some cases, that's not always easy to do because sometimes in low signal to noise cases, it's easier to fix or assume a fixed light profile. And so we have these bulge and disk fluxes that assume a Cersic index of 1 for the case of a disk. So these are like exponential disks that are very shallow, or Cersic index of 4, which is like a bulge de Vaucouleurs profile. So we have those available too, so that people can assume the same light profile shape for the sample that they're looking at. And then we have the composite model fluxes, which are essentially a combination of those two. So you assume a two-component Cersic model with a bulge component and a disk component. So generally, I think the recommendation is that either Cersic fluxes or C model fluxes, all other things being equal, are sort of a best case. In the absence of other specific things you want to do, I think both of those parameters work fairly well at recovering the total fluxes of galaxies. Okay, so the first thing we can do is just compare these different measurements. I mean, these different measurements assume different things, and so they're going to return different photometry for galaxies. So the first thing I'm going to do is compare the C model flux to the Cersic flux and to the BD fluxes for a subset of galaxies that we collected. So here I'm going to make a plot that basically just plots these different parameters against each other so you can see how they perform. All right, so this plot that comes out is showing the C model magnitude compared to another magnitude. So in red, this is compared to the BD flux assuming a bulge profile. The blue is showing the BD flux assuming a disk profile, and then the green is just a single Cersic profile. And so what you can see here is that for a sample of galaxies, the Cersic and the C model are pretty comparable to each other. The median is 0. And so you can see the median and the difference, I mean, is 0. So they basically return the same flux for the majority of objects. There's a lot of scatter over towards the very faint magnitudes because it becomes harder to sort of measure photometry near the signal to noise limit. One thing to point out here is that if you assume a fixed Sursic profile, you may under or overestimate the flux compared to one of these sort of more um, tailored measurements that lets the Sursic index go free or scales the relative contribution of the disk to the bulge and things like that. So here you can see kind of one of the consequences of assuming the bulge or disk, which is you may over or underestimate the flux because you made an assumption about a fixed light profile shape. And so this sort of demonstrates what I said before, which is that the C model and the Sursic model fluxes are kind of your best, the sort of best estimates of total fluxes for galaxies. Okay, let's see. This one is now showing how these things compare as a function of Sursic index. So this plot is showing Sursic magnitude compared to another magnitude. So in this case, in blue, again, we have the disk, bulge disk, but the one fixed with the Sursic index to be 1. Compared to the one where it's assumed to be a bulge. And so I've plotted this as a function of the Sursic index n that was used to measure the Sursic magnitude. And so you can see that for very high Sursic index, when you get closer to the one assumed for the bulge, you get sort of, you approximate the Sursic magnitude. And as you go to much lower Sursic index like that, which is assumed when you measure the disk magnitude, then you get sort of the same as the Sursic magnitude. So for these different use cases, you can kind of get a sense of how these things are performing and how the different measurements relate to each other. Okay, so in the interest of time, I'm going to skip over this apparent fluxes, other than to say there are a number of fluxes in the object table that do not get corrected for losses outside of the aperture. So sometimes when you see cron fluxes or circular aperture fluxes measured from images, sometimes those things get corrected to a total using like a PSF correction, for example. So that correction is supposed to take into account the loss of light on the outside of the aperture, because when you do an aperture photometry, you're basically adding up all the flux within the aperture. To get a total magnitude, you would need to go add a correction for the loss outside of the aperture. The object table does not include that correction. So there are some measurements in there that are not total fluxes. These include the cron flux and the circular aperture fluxes. So that's just something that's important to be aware of. These things have their own science applications, and so there are some use cases where those are more usable than some of the other measurements that are included. But anyway, I'm going to skip over that just because I think they're sort of less broadly applicable for galaxy science. And I'm going to skip over to the end where I'm going to talk about photometry measurements that are useful for making color measurements of galaxies. And so I mentioned this earlier, this GAAP flux, which is contained in the object table. This stands for Gaussian aperture and PSF flux. There's a whole paper written about the method. I like to think of this as like, if you have small number of images, you can PSF match those images to the largest PSF size if you're trying to compare colors across different images. The longest wavelength will have the largest PSF, and so by PSF matching, you're making a correction so that you can robustly compare colors across different PSF sizes. So this Gaussian aperture and PSF flux attempts to do this so that you can robustly compare colors across these different images with different PSF sizes. So here I'll just quickly make this plot. This is showing the C model magnitude, which we were talking about earlier, compared to another magnitude as a function of the cron radius. So you can think of the cron radius as just sort of a metric for the size on sky of a galaxy. So it's not perfect, as I will show in the next notebook, but if you need like a quick measurement of like, is this thing very large or very small, then you can use that. So this is showing the GAAP 1.0 aperture flux in orange, and then in blue, I'm showing the cron compared to the C model. And so you can see both of them are sort of not quite in total, they're not measuring total photometry, and you can see that they don't really line up with the total photometry. But that's not the purpose. The purpose of the GAAP flux is, for example, if you want to do color magnitude diagrams. And so as a quick demonstration of that, I'm going to do another query here. So ECDFS, which is the sample of galaxies we just looked at, those galaxies are from a blank field. So there's no large scale structure in the foreground of this of that field. But we did also target a cluster in one of the DP1 fields. So I'm going to query that. That cluster is the Abel 370 field. And so this is its coordinates. So I'm going to query a different DP1 data set to collect the same photometry of galaxies in that field. So I'm going to run this query here and store the results in this table called table 2. And then I'm going to collect the GAP magnitudes from both the field, so the ECDFS is labeled as field. So I'm going to do a color magnitude diagram using the GAP colors and the C model magnitude. And then I'm going to do that also for the cluster field. So I've stored all of these so that I can make a color magnitude diagram, and that's what this is going to do. So this plot first is going to plot the color magnitude diagram for the field galaxies in the ECDFS in blue. So this is G minus I color using the GAP fluxes, and the I band magnitude using the C model fluxes. And in the bottom panel, I'm showing this Abel 360 cluster field. Again, the G minus I color versus I band magnitude. And so the galaxy clusters typically have these red sequence galaxies in the foreground. And so there's a lot of those. And so you can see when you compare the color magnitude diagram of these cluster galaxies to that of the field galaxies, there's this very nice red sequence that pops out in the cluster galaxies. So this is just a demonstration of how you would use the GAP fluxes to make, for example, a color magnitude diagram. Okay, I will pause briefly here to see if there's any questions about photometry. Yes, Andres.
Um, I've seen that in SDSS they had hypertrophian magnitudes. They don't use that anymore. We don't use that anymore.
No, but I couldn't tell you why they decided
Okay.
not to do that.
Okay, that's okay.
But maybe someone else knows the answer.
I think the Petrosian kind of fell out of favor. Uh, the exact details I don't remember. I mean, it was good for the time. Even during STSS, towards the end, they was trying to use C model and things like that as
Right.
opposed to Petrosian.
Right. Okay. Okay. I'll.
But yeah, I don't remember the details. But yeah, I mean, Petrosian is better than some of the alternatives, but it's no longer considered the best. I have to admit, I don't quite remember why. I think it depends on the type of galaxy and how much flux you get in the outer parts, whether it's elliptical or
Yeah.
spiral. I think there is some variation.
Okay. Yeah. Thank you.
Okay. Any other questions? And if not, you can always ask questions about this notebook after I do the next one also. Okay, I'll just move on and then we could take sort of general questions afterwards. So to open the second notebook on galaxy shapes, we go back to this tutorials menu option and go to DP1, and we're going to go back to this 303 galaxies category and open this galaxy shapes notebook, the second one. All right, so here is the galaxy shapes notebook, and again, there's this preamble that sort of orients you to what we're going to do. So in the object table, I showed the photometry. A lot of the photometry actually does rely on some characterization of the shape of galaxies. And so those shape parameters are also stored in the object table, although they're a little less straightforward to use. So I'm going to try to go through them and how you grab them out of the object table. All right, so there's some information here. There's going to be more packages that we're going to import here because some of the shape parameters actually rely on some of these other LSST pipeline tools that that we didn't need in the last one. But a couple of things that I'm going to call out here. Actually, let me just go through them at the top. So we have NumPy and Matplotlib, like I showed in the last one. There's a few things, other things that we need because I'm going to make some image cutouts of the DP1 imaging in order to sort of demonstrate how to show that the shape parameters look like the images that we pulled out. So in order to do that, we have to grab a certain number of like virtual observatory like packages. So some of them are here. This is the in order to access the images at the Rubin Science platform in the Rubin database, we have to be able to authenticate these images because they're proprietary. So we have a few things. I'm not going to really focus on those. We have another notebook tutorial that demonstrates how to do these things, but I'm just going to grab some of these packages that is going to enable us to authenticate with the Rubin database so that we can pull these cutouts back. So these all contain basically everything here is doing that. I'm pulling up also a few AstroPy packages because I want to display some of these shapes on top of the images, including the WCS. And then I'm going to import Photutils. So Photutils is also an independent package that enables you to sort of do aperture photometry, but as a consequence, you can also draw apertures on top of images. And so that's just an easy way to sort of demonstrate that the shapes line up with the images. I'm also going to import this thing called GalSim. So GalSim is a simulation package that was used by the LSST project in order to generate the data preview 0.2 and 0.1 images. So I'm just going to pull that up because it contains some packages that help us use the object table entries in order to make actual shapes that we can understand. And then I'm going to also import this Gauss 2D package from the LSST pipelines, which will help us to convert. As you'll see, some of the shape measurements that are in the catalogs need to be converted into sort of shape measurements that we are all familiar with, sort of from GalFit and other types of measurement codes. So I'm going to import these packages, and I'll mention that later. Okay, so I didn't run that yet, though. Okay, so the next thing I'm going to do is just make this very quick function called make image cutout. Don't worry about the details in here. This is just a way, it's just basically a wrapper function to enable us to make a cutout of a Rubin image so we can look at individual galaxies. So I'm going to compile that function. I'm going to make a couple of just define some norms throughout this notebook to be colorblind friendly and to also be able to display things in the notebook using Matplotlib. All right, so like I did last time, I'm going to start an instance of the table access protocol or TAP service. So we're going to query the object table using this TAP service. And like the last time, I'm going to find a collection of galaxies in the ECDFS. So here are the coordinates for the ECDFS. And now I'm going to query the object table again. This time, instead of collecting all of the flux measurements, I'm going to collect mostly shape measurements. So here, just to highlight a few things, I'm going to get the object ID, the RA and DEC again. I'm going to ask that I'm going to ask for galaxies by setting this flag extendedness equals 1. I am going to also set some flags, force some flags to be 0, which means that the measurements are good. So I have some shape flags, the Sursic flag, and a cron flag to make sure that all of the measurements that we return are going to be good and there wasn't some problem with the measurement. And then I'm going to request a number of shape measurements. So I'll just highlight a couple of shape measurements here that I think that we're going to use. So we're going to use these shape XX, shape XY, and shape YY. These are moments, and I will show you later how to convert these into sort of ellipse parameters that you might be more familiar with. We're also going to return this IXX, IXY, and IYY parameter, which is, again, another type of shape moment. And then we're going to collect the Sursic index, the Sursic effective radius in the x-axis direction and in the y-axis direction, and then this row parameter. And I'll show you how to sort of convert these into Sursic parameters. All right, so I'll set up this query. I'll run the query. And then I'm going to store the output of all these shape parameters in this table. So here you can see there's, so in the request I made, we ended up with 45 objects that we can work with. So you can see all of the columns returned and all of these different shape parameters. And so we'll go through some of those shape parameters and show you how to access important shape measurements from that. Okay, so the first thing I'm going to do is pick one object that, so some of these shape measurements are not always very accurate for very small and very faint objects. So I'm going to I picked in advance a very large object with a very ellipsoidal shape as a good demonstration. So I already know what the object ID of this thing is. So I'm just going to store the object ID and define some coordinates for this object ID so that we can make an image cutout and store the center of the source. So here I'm just going to set the image has a pixel scale of 0.2 arcseconds per pixel, so I'm just going to set this as a convention because a lot of the measurements in the object table are made in units of pixel, and we're going to want to, okay, we're going to want to plot them in arcseconds, so we need to know this conversion. So the first thing I'm going to show is how to reconstruct the Gaussian ellipse. So there are these shape IXX, IYY, and IXY. You may recognize, if you're a weak lensing person, you may recognize these as the re-Gaussianization method. So these are moments. We have to convert those into things like the position angle and the size and things like that. So one of the things I'm going to show is how to reconstruct that. These are measured on, and also, so this is in the I band, I should say. These are measured on each individual filter separately, but then there's also this shape parameter is stored on measured on the reference band. The reference band is sort of taken as the one that is the place where we could measure the measurements the best. And so we have these shape measurements that can be used to reconstruct that. So these shape measurements by themselves don't have a lot of intuitive meaning. So we have to convert these using some of the LSST packages in the ellipses package. So I'm doing that here. We're basically feeding the moments to this ellipses.quadrupole package, and then we're going to return measurements that we're maybe more familiar with using this axes package. And so you can get the semi-major axis, the semi-minor axis, and then theta, which is the sort of rotation angle of this 2D Gaussian that was used to measure the shape of this galaxy. So I'm going to run that. I also show here a second way to do this. So there's an equivalent package called lsst.gauss2d where you can use that to reconstruct it, but the sort of syntax for doing that is slightly different. But the measurements are basically the same. So here, this is ellipse major, and you have to feed it the parameters, the shape parameters according to this syntax. And so then you store the semi-major axis, the semi-minor axis, and then the rotation angle the same as you did before, but with different nomenclature. But you can see that the output of those two are identical. So these are equivalent things you can do. So now I'm going to use photutils to just generate an aperture that visualizes this shape, this 2D Gaussian shape. So to do that, I'm going to give this sky elliptical aperture is it's going to define an elliptical aperture on the sky in WCS coordinates. I'm going to give it the center, the semi-major axis in arcseconds, the semi-minor axis in arcseconds, and then the rotation angle according to its convention. It wants the convention to be a certain direction, starting with defining the zero angle as in a certain convention. So that's what sometimes you may see plus or minus 180 or plus or minus pi over 2 to make sure that the conventions are the same. All right, so I'm going to generate this Gaussian elliptical aperture, and I will pull this up later when I visualize all these apertures. Okay, second, I'm going to do the chronellipse. So I mentioned earlier, chronellipses are, you can do an ellipsoidal aperture to measure the photometry of galaxies. And so sometimes it's useful to know whether or not the chron aperture is collecting the majority of the light in a galaxy, or at least how the Gaussian aperture compares to the actual light of the galaxy. It can give you some sense of whether or not we lost flux on the outskirts, or whether it was too big and it included objects that were neighbors that is adding flux, because the cron photometry, these aperture photometry do not attempt to like remove the neighbors. And so anyway, so this is useful to know. So the cron radius is something that's stored in the object table. So we get this cron radius. But the cron radius by itself is not, in order to get the aperture, you need to convert the cron radius into in a specific way. So I'm going to just demonstrate here how you do that. So we're going to take the semi-major, you need to get the, I guess, the circularized moment radius, which is defined as the square root of the semi-major times the semi-minor axis. So we got that from the 2D Gaussian ellipse measurement. So we can generate this moment radius for the cron aperture here. Then you can define the cron aperture semi-major and semi-minor axis using the cron radius, the semi-major, semi-minor axis, and also the moment radius. And then the convention of the aperture photometry in the cron aperture photometry in the object table is to take 2.5 times the radius, because this has been shown to sort of, in a statistical sense, collect the overwhelming majority of flux from galaxies. So this is just a convention that's used in the literature. All right, so I'm going to do that, and then I'm going to define the cron aperture in the same way as I did before with this sky elliptical aperture. So I'm going to give it the semi-major, semi-minor axes, and then also the rotation angle. So now I'll pull up this cron aperture later. In the meantime, the last thing I'm going to do is show you how to convert the Sirsic shape. So this object table stores a number of Sirsic parameters, but it's not sort of the ones that you need in order to reconstruct the Sirsic profile. So again, we need to convert some of these parameters using some of the LSST packages like ellipse or ellipse major. So the things in the object table include the half-light radius in the X direction and the half-light radius in the Y direction. That's not really what we want. What we want is the half-light radius in the direction of the semi-major axis and the semi-minor axis. So there's a rotation parameter rho, which helps you to convert the X and Y into the semi-major and semi-minor. And the output of this will give you the BA, which is defined as B over A. So it's the semi-minor over semi-major axis when you call, so for example, B is often referred to as the semi-minor axis size, and A is often referred to as the semi-major axis size. So we've defined BA to be this axis ratio. Then we define position angle to be the rotation angle of the galaxy, and then we define this R major to be the semi-major axis of the Sirsic profile. And then you can use, again, phototils to generate this Sirsic profile using the semi-major, semi-minor, and rotation angle. And this will give you sort of the half-light Sirsic aperture to show you the half-light size of the galaxy. Okay, so now we're gonna go, I didn't run this. Hang on, let me run this. And run this. And then now I'm gonna generate a cutout. So we're gonna call this make image cutout function that I skipped over in the beginning. I'm just gonna give the cutout size this in degrees, so it's a relatively small aperture for the cutout right around the size of the galaxy. And then I'm gonna give this galaxy that we picked out as a good candidate for demonstrating these shapes. I'm gonna give the coordinates there. And I'm going to generate, using the Rubin cutout service, I'm going to generate this cutout object that we can then plot apertures on top of. Okay, so now we have the cutout, and now I'm just going to plot the cutout here. Here. I'm going to just make a box. Here I'm going to display the image. So the cutout, to get access to the cutout, you do this .image.array extension to get the science image slice of that cutout. And then I'm going to plot these three apertures that we defined earlier. Okay, so here you can now see the galaxy that we picked is a big elongated edge-on disk-looking galaxy. It's very large. So the cron photometry and apertures don't typically work very well at very small size and very faint magnitude, so we needed to pick a big one. You can see here the cron aperture. So this is a very, very stretched image. So you see in detail the low surface brightness features. But one thing to point out here is that the crown aperture, as reconstructed, is actually missing a significant amount of flux on the outskirts of this galaxy. So this is a good candidate for using, for example, C model or Sursic model fluxes, because those fluxes will include this low surface brightness that has been modeled by the shape modeling. So here you can see these are now in blue and in orange are showing the Gaussian shape ellipse and the Sursic ellipse. But remember that these are like the half light or the full width half max shape. So these are not apertures, but this sort of gives you a general idea of the steepness of this light profile. So the half of the light is contained inside these small ellipses in these models, and then half of the light is on the outside. But anyway, you can see here that these, so these are measurements of the half-light size, basically, of this galaxy. But anyway, this gives you a sense of how you can access these shape measurements from the object table and reconstruct them into sort of user-friendly parameters that you may be familiar with. Okay, I only have a few minutes left. I just want to show one last thing. You can also generate, sometimes it's useful to see the model of the galaxy that you are using so to measure the total flux, we've taken a Sursic model and then added up all of the flux in the Sursic model. So sometimes it's useful to compare the Sursic model to the image to make sure that it looks like the image. So this cell here is just showing you an example of how to reconstruct a model, and it's the model that was used to measure the photometry so that you can then compare it to the actual image. So here is a model of the galaxy that was used to measure this is the Sursic model. So adding up all of the pixels values in this image would give you the total flux. So you can see here, I summed up all the pixels in this image. It came out to this amount of nanojanskis, and that's pretty close to what is given in the object table, which is here. So this is a nice sort of verification of how the photometry is working. So you can kind of go back and look at this galaxy and see that the Sursic model looks similar to the galaxy image. So that's all I have. There are, at the end of this notebook, there's also some sort of known issues that are useful to be aware of as you sort of explore the shape parameters in the object table. So so maybe we can take questions in the last few minutes. Or if there's no questions, that's fine too. Okay. Well, if questions come up later, you can always feel free to post them on the forum or bring them to the drop-in session next week. We're going to have a drop-in session at this time slot. So that's an open forum for you to come ask questions or bring issues you're having with the Rubin Science platform. Like if you're trying to do something and you know, it might be that community science team members can help sort out problems you run into. So. Oh, yes. And this session is recorded and we're going to post this once it gets uploaded to YouTube. So there should be an announcement if you watch the forum post, you'll see probably in the next few days, the recording will be posted there. So yeah, thanks for that reminder. All right, well, thank you everyone for coming. We'll see you next time.